Okay, so okay, so so I have to describe today one error correction technique that we developed for the earlier one for correcting errors in DNA storage. So before that, I need to tell you a mathematical fact, and the sort of the next method is more or less based on the similar lines. So I need to describe that. So suppose, so I want to show you the one fact that if C is a T error correcting code, then minimum distance of C, minimum means minimum Hamming distance I am talking about, is at least 2T plus 1. Okay. So C is our NKD code, means our k-dimensional subspace of the vector space, and it is a T error correcting code if minimum distance of C is at least 2T plus 1, and I can establish the fact. So the proof is important here, and you will see that similar lines actually we proceed in the DNA storage. So what I need to do, suppose X is a vector that is sent and Y is received. This is our channel, noisy channel, right? Now T errors have occurred. Okay, so that means distance between X comma Y cannot exceed T, right? X is sent, Y is received, T errors have occurred, so they will flip at T places. So distance between X comma Y, the number of places they differ, Hamming distance cannot exceed T, right? Fair enough. Now, we know that the minimum distance of C is 2T plus 1. So let us look at what happens inside our C. X is a vector which was sent, and suppose X prime is another vector in C. Then we know that the distance between any two vectors in C is at least 2T plus 1, right? So this distance is at least 2T plus 1. Okay. Now, X is a vector which is sent, Y is the vector which is received, and we know that the distance between X comma Y cannot exceed T. Now, very important, look at it very carefully. My claim is, so now, first of all, just tell me, when do you think we will be able to correct the errors? X is sent, Y is received, and what you normally we do, we compute the distance of Y with all the vectors in the C. Whichever is the least, I decode it like that, right? So obviously, we want to show that the distance of Y with X is the smallest, right, as compared to all others. Right. So now my claim is, since X prime, suppose X prime is a vector which is not equal to X, so distance between X prime and Y. My claim is this should be more than T. Because then only we will be able to correct it, right? If this distance is more than T, then we are able to correct, because all other, so basically what it says that distance between received vector Y and the one which was sent is at most T. For all the other vectors, the distance of received vector with all other vectors is more than T. Then we will be able to correct, right? It's a very natural thing, right? Now, so proof is very simple based on this fact that the distance between any two vectors is at least 2T plus 1. Now what happens? Suppose not. So our claim is the distance between X prime and Y is more than T. Means it is at least T plus 1, right? Right? I mean, if it is bigger than T, it will at least T plus 1. So suppose not. Suppose this is less than. Suppose I am assuming a contradiction. Suppose this is less than or equal to what? T plus 1, right? Suppose this is less than or equal to T plus 1. So I am assuming that the distance between X prime and Y, so in other words, I am saying the received vector Y has distance less than or equal to T plus 1 from all other vectors in C other than X. Now, what will be the distance between X and X prime? I can compute that, right? This will be less than or equal to distance between X comma Y plus distance between Y comma X prime. A triangle inequality of the distance. Now this distance is less than or equal to T, correct? And distance between Y and X prime, I have assumed it is less than or equal to T plus 1, right? So this is less than or equal to T plus 1. The whole distance is less than or equal to 2T plus 1. That means I am able to show that distance between X, which was sent, and any other vector in C is less than 2T plus 1, which is a contradiction to this fact. Right? That is because the minimum distance of any two vectors is at least 2T plus 1. Got it? Right? Yes. Yeah. Still the result will be true, right? This will turns out to be 2T then, right? Fine, that's okay. I mean, one case is there, right? Fine. So basically, what it shows that if X is sent, Y is received. This is very important observation. Basically, you need to remember that the distance of the received vector with any other vector other than X is more than T. That is the fact. If we are able to correct the errors, right? Now, this simple observation we are going to use actually. Okay. Fine. The similar technique we are going to use. Let me show you. I think we already looked at these things here. Yeah. So remember, we were looking at this map. Now I am actually claiming that using this map, we are able to correct 2-bit flip in the system. Otherwise, we were able to correct only one, but here now we will be able to correct 2. So how is that? You see. So first of all, if X in a DNA storage thing, if X DNA is sent, Y DNA is received, T bits are flipped. That means distance between X DNA and Y DNA is T. Then the corresponding ternary code words have distance at most 2t, right? So this is the observation. I think you can see here clearly. This is the fact in this example. Now, this is the proof of this lemma. I mean, so this is a, based on the similar ideas what I told you just now. Using double layer error correcting scheme, we can correct any 2-bit flips in DNA. Okay, so now you see how. Suppose XDNA is sent, means is written, and YDNA is received, right? Such that there is a 1-bit flip. A become T or C become whatever, 1-bit flip is there, right? Now what happens? Case 1. If there is a 1-bit flip in DNA, the Hamming distance between XDNA and YDNA will be 1, right? Correct? Because there is a 1-bit flip, XDNA is sent, YDNA is received, and there is only 1-bit flip. That means when we go to the ternary system, actually this becomes 2. You just saw the example here, right? If the distance between 2 DNA vectors is t, then the corresponding ternary vectors have distance at most 2t, right? Right. So that means, in fact, in some cases it is exactly 2t, right? For example, in this case, you see. So here, so this, in this case, in ternary vectors, weight distance is 2. Now, ternary code, what we have used is ternary Gole code. So there the Hamming distance is 5. So 5 means how many errors we can correct? 5 minus 1 by 2. That is how much? 2. Distance is 2. We will be able to correct these things, right? So case 1 is very simple. Using the standard fact of classical coding theory from over ternary codes, right? We will be able to correct 1-bit flip in DNA. So 1-bit flip in DNA corresponds to 2-bit flip in the ternary, right? And ternary Gole code system, that subcode which has distance 5, will be able to correct that, right? That is okay. Now the other side, if the distance between XDNA and YDNA is 2, now what I am going to show you is it is basically based on this property of the map actually. And this is something really interesting. So now distance between XDNA and YDNA is 2, then there exists vector X in C, Z3. You basically look at cDNA, which is consisting of all DNA code words. You map it to the ternary one, you get this set actually CJ3, right? And Y is a receive vector which will be somewhere in the space, in the ternary space, right? And the distance between X, Y cannot exceed 4 because of that lemma, because it is right. Fine. Now, here is something like this: XDNA is sent, YDNA is received, read write channel. So now we look at the set here. Okay, when we look at so basically, now I want to show that received vector Y has distance more than, right, whatever is required, right, for the error correction. Okay, so now that is what I'm going to show you here. So basically, I want to show that for every WDNA, which is not equal to XDNA, XDNA is the vector which was sent from the code. We claim that the distance between YDNA, the received vector in the DNA storage channel, with any other vector in cDNA is more than 2. And you see how it, there's an example I can show you. So what happens? You see, XDNA is this, YDNA is this. So corresponding ternary vectors are X and Y. With that map, you can do that. Now, the minimum Hamming distance between XDNA and YDNA is 2. And of course, the corresponding ternary vectors have distance 4. So the problem is that now the distance between X, Y is 4. I will not be able to correct it using the ternary code because ternary code has distance 5, right? I will not be able to correct 4 errors, right? Here actually, this map is allowing us to correct that. So what is happening here? You see that this is the all vectors, the set, and you can see that you see all other vectors have distance more than, you see that WDNA and YDNA. YDNA is the received vector in DNA The Hamming distance between WDNA and YDNA is exactly 2 with the one which was sent, right? For all others, it is more than. Got it? So I gave you just an idea how things are happening, right? This is a very clever, I mean, very interesting observation of this map actually. So first of all, I should tell you again that, the Gole code, we are using a sub code actually. It is not the entire thing. So if you see, here is a map, right? Yeah, this is the map. So we are using this code, which is a sub code. That means if you take two ternary vectors, there some may not be in the set. It's a nonlinear code. Okay. We are using this map because there are 256 vectors, each mapping to the 256 XC characters, right? Yeah, this is ternary Gole code. No, so this is the ternary Gole code. You see the generator matrix of the ternary Gole code is this. I mentioned to you last time. This is the generator matrix of the ternary Gole code, right? And in fact, if you puncture it, we get 1165 ternary Gole code. And from this puncture code, we get 729 code words. Out of this, I am only selecting 256 vectors. Okay, and which are these vectors? Length 11, 256 vectors, and distance property will remain the same because, right, we are just taking only subset of it, right? So minimum distance is 5. So when there is a single bit flip in the DNA, we are able to correct 2 errors at the ternary level using this code itself directly, right? If there are 2 bit flips in the DNA, there will be, that means 4 bit flip in the ternary. There actually we are again going back and correcting it through this map. The map is allowing us to correct that, right? Okay, so this is the nice property. And I think if you want to read more about it, you can look at the paper anyway. So we talked about it. Actually, you can also compute the capacity formula. So by the way, now as a tea time problem, I have not given you tea time problem since long. So what I suggest, how to obtain this formula. Look at the paper actually, at least you can see, right? How to arrive at this formula. Based on the chunk architecture, you can find out this formula. That what is the capacity, how much capacity per gram of DNA. Whenever you are using any codec, you can determine what is the physical density. Okay. So using the chunk architecture, you can do that. It's not very difficult thing. So I'm just probably high school mathematics calculations, right? So I leave it to you to compute that now. With this method, we are able to store 150 exabytes per gram of DNA. Okay. Now you see that there is a different. So we have tried different things, 11 one and then different length, and you can see that this was the Goldman. The cost is too much, and ours are almost, of course, it is not very linear, but at least that sense, so our scheme is much better because all the 5 things that we've chosen, they are working good in this direction. And if you look at the code rate, normally, rate should be as close to 1, right? Those are the good codes. But you see, if you look at t is equal to 2, the code is very close to half. And if you increase the error correcting capabilities, you see the code rate goes down. So it's really not much useful. So this is the best option that we can have, right? So different families, there are 5 different families other than ternary Gole code, which you can try actually, right? So that is the thing. And you can see that there is a significant improvement in terms of number of chunks, number of nucleotides as compared to Goldman results. So this is the modification of the Goldman paper initially. Right. Now, what I can do is the following. I think before starting this paper, maybe we'll talk about it later on. Okay. So now, keep it. So question is quite easy. I hope you will be able to do it nicely, right? Number one, number two. So find standard G generator matrix, right?